Okay, this video is going to show us how to use calculus to make a complete sketch of the curve f of x equals x to the fourth minus 4x cubed. And this is an example of a polynomial function. All right. For another video on how to do, or I will post another video on how to do a rational function. So this one is for polynomial functions. All right, so it could be a cubic function, a fourth degree, a fifth degree. All right, but it'll be in the form f of x equals ax to the whatever plus bx to the whatever, yada, 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 in descending order. So the first thing we're going to do is we're going to find the intercepts. So to find the x and y intercept, I am going to use f of x. Okay, I'm going to look at the original function. So the original function says f of x equals 4, or x to the fourth minus 4x cubed, I believe. Yep, x to the fourth minus 4x cubed. So I have x to the power of 4 minus 4x to the power of 3. And I am going to do the x-intercept first, where I let y equal 0. So I'm going to replace the f of x with a 0, and then I am going to solve for x. Now, in order to solve for x, I'm going to need to factor the right-hand side here. So what can I factor here, or how can I factor x to the fourth minus 4x cubed? I can take out an x cubed. All right, I'm going to just do a common factor. Both of these terms have an x in them, and I take out the lowest degree, or the lowest exponent. So I would take out an x cubed. So x to the fourth divided by x to the third would leave x to the first, minus 4x cubed divided by x cubed would leave a negative 4. Now, because of the zero product principle, I've got these two factors, x cubed and x minus 4, and they're multiplying together to give me a 0. That tells me that either x cubed equals 0 or x minus 4 equals 0. Take the cubed root of both sides, I've got x equals 0, and add 4 to both sides, I've got x equals 4. These are 2 points, all right? This first point is 0, 0. This next point, x is 4, y is 0. I have 2 x-intercepts on that curve. Let's move on to the y-intercept. And for the y-intercept, I'm going to let x equal 0. Y-intercepts are much easier than x-intercepts. F of x equals x to the fourth. Again, I'm using the original function. And this time, I'm going to replace the x's with a 0. I think you can probably figure out pretty quick what this is going to equal. 0 to the fourth is 0. 0 cubed is 0. So I have 0 minus 0 gives me 0. That point would be 0. X is 0. Y is 0. And it's the same as this x-intercept. Now we're going to look at something called symmetry. Symmetry, there's a little test to see if a function is symmetric. And again, for symmetry, we are going to use the original function, f of x. And I'll just write a little note over here. A function is odd if f at negative x is equal to negative f of x. A function is even if f at negative x equals f of x. If it doesn't satisfy one of those two situations, then it's neither. It's not odd or even. And really, symmetry is just a way to kind of shorten up the curve sketch. An odd function is symmetric about the origin. So it's symmetric about the origin. And even functions are symmetric. So it's symmetric about the y-axis. And you can look at your notes on symmetry in the Teams page for a better explanation of that. But here we'll do the test, okay? So what I'm going to do is I'm going to take the f of x function, and I'm going to replace all the x's with a negative x. Okay, maybe I'll do that in red. So I'll have negative x to the fourth minus 4 times negative x cubed. And I'm just going to work this out, and I'll see if it satisfies either of the two constraints listed above. So f at negative x is going to equal negative x to the fourth. 4 negatives multiplied together would give you a positive, so you get a positive x to the fourth. This would give you a negative x cubed times a negative 4, which would give you a positive 4x cubed. Now let's examine these two things. Does f of negative x, does it equal what we started with? Well, x to the fourth are the same, but no, it doesn't, because now I've got a positive 4x cubed, and here I had a negative 4x cubed. So because f of x, or f of negative x, does not equal f of x, we can say it's not even. And we can also see that f of negative x does not equal negative f of x. Now, in order for that to be true, both of these signs, the original signs, would have to be changed. So this would have to be a negative x to the fourth and a positive 4x cubed. That's telling you to take the f of x function and multiply the output by negative 1. So multiply all the terms by negative 1. That didn't happen either. Only this sign changed. So we'd say it's not odd. Rather than saying all this, okay, you could just say there is no symmetry. I'm just showing you that for the purpose of this video. Okay, so we've got our intercepts and we've got our symmetry. Now, for the asymptotes, these will only occur when we're looking at our rational function. So there'd be no asymptotes for a polynomial function. And in order to do that, we would also look at f of x, but because it's polynomial, this does not apply. Not applicable for polynomial functions. Good news, I can speed up the process and move right on by. For the intervals of increase and decrease, and I'm just going to take this info and scoot it out of the way. If I can. How about this? Don't need it anymore. Pause the video if you want to see that, or rewind it. Okay, let us look at the intervals of increase and decrease. Now, in order to do this, we need to work with f prime x, the derivative. Okay, so when I said in the beginning we're going to use calculus to sketch this polynomial function, this is where the calculus part comes in. All right, I'm going to use the derivative in order to find my intervals of increase or decrease. Intervals of increase, it means your y values would be getting bigger, the function would be rising. Intervals of decrease means your y values are getting smaller. It also means that intervals of increase, the slopes of your tangent lines are positive. Intervals of decrease, the slope of your tangent lines are negative. I encourage you to look at the first derivative test, okay, or the section on intervals of increase and decrease in your Teams app. All right, I've posted the files there. So for the intervals of increase and decrease, we need to use f prime x. So I'll just make a little heading here, intervals of increase / decrease. And f of x equals x to the fourth minus 4x cubed. All right, to do the derivative of this, pretty simple, just a little sum and difference rule. The derivative of x to the fourth would be 4x to the third. The derivative of negative 4x cubed would be negative 12x squared. So the reason we did derivatives first is because now we can apply them to this curve sketching process. And what I need to do is I need to determine my critical values. All right, the critical values of this derivative. Those are the values of x that would make the derivative equal 0 or make it undefined if it were in the form of a fraction. That would make the bottom 0. Not applicable here again because it's a polynomial function. In order to find the critical values, I'm going to factor this. So I will take out a 4x to the power of 2. Divide both of these terms by 4x squared. 4x cubed divided by 4x squared leaves an x. Negative 12x squared divided by positive 4x squared leaves a negative 3. Now, I'm going to set this equal to 0, and I am going to solve for x. So I'm going to take each factor and set it equal to 0. And I'll solve. Divide both sides by 4 over here, and I'll get x squared equals 0. Take the square root of both sides. Okay, the square root of 0 is 0. Just be careful if this were a number like 9. Okay, a lot of people will write x equals 3. The square root of 9 is 3. That's true as the principal square root, but x could also equal a negative 3. You'd have to make sure that you would write both critical numbers or critical values. On this one, I'm just going to add 3 to both sides. So my critical values are x equals 0 and x equals 3. These critical numbers are the potential locations of maximums, what we call local maximums or local minimums. And again, you can see for more information on that, look in the Teams app. But what I want to do is I want to find the intervals of increase and decrease. So I'm just going to draw a little number line next to my derivative. I'm going to mark my critical values on that number line. So I'm going to put a 0 and a 3, these numbers right here. And what I'm going to do is I'm going to test each of these intervals. So you might say, well, what are the intervals? All right, well, check this one out. It goes from 0 to the extreme left. Well, if you think of the extreme left of a number line, you're heading towards negative infinity. So this first interval goes from negative infinity to 0. This next interval goes from 0 to 3. That one's very obvious. And then the third interval goes from 3 to infinity. What I want to do is I want to pick some test values. Now, any number between negative infinity and 0 would work here. I'll go with negative 1, but you could use negative 10, negative 100, whatever you want. What I do with this is I plug it into the into the derivative, and I'm testing to see whether this would work out to be a positive or a negative. Okay, so let's think about that. Again, you don't have to know exactly what it equals, but if I plug a negative 1 into the derivative and I square it, I get positive 1 times 4. This factor right here would work out to be a positive 4. This factor right here would work out to be a negative 4. So I'd have a positive 4 times a negative 4. Again, that's negative 1 squared, 1 times 4 gives me 4. This factor would be negative 1 minus 3 gives me negative 4. So a positive times a negative means that my derivative would be negative. So I'm just going to write a little negative sign above here. And that would be true for any x value that I picked on this interval from negative infinity to 0. That also tells me that my function is decreasing on this interval because my tangent lines, the slope, or my tangent lines would have negative slopes. So the function would be going down like that. Y values would be getting smaller. Next, I'm going to test something between 0 and 3. I'll test a positive 1. Okay. If I plug a positive 1 in here, check this out. 1 squared is 1 times 4. This factor would work out to be a positive. This factor, 1 minus 3, would be a negative 2. So I'd have 4 times negative 2. It would give me negative 8. That still means it's decreasing on this interval as well, from 0 to 3. So you could say it's decreasing from negative infinity to 0 and from 0 to 3. Or sometimes people will just say it's decreasing from negative infinity to 3. Next one I want to do is test this interval right here. I'll test the 4. Okay, you could use a 5, a 20, something between 3 and infinity. But if you plug a 4 in here and square it, 16 times 4 is 64. 4 minus 3 is 1. Positive 64 times a positive 1 gives you a positive 64. And again, I don't care that it's a positive 64, I only care that it's positive. So here's what I can write. I can say it's decreasing on the intervals that have negative signs above them, so from negative infinity to 0, and from 0 to 3. So I'm just using interval notation. That represents not an x and a y, these are two x values. You also may write it like so, decreasing from negative infinity to positive 3. The interval with the plus sign above it, well, that's where it's increasing. Okay, that's where the slope of my tangent line, the derivatives, are positive. So a positive slope would look like this. Right, that means my y values would be increasing. So it's increasing on the interval from 3 to infinity. Now, the first derivative test tells us that if a function goes from negative, or if the derivative goes from negative to positive at a critical number, like it does here, we have a local min. Okay, I'll do that in green. This would be a local minimum. Now, if there were a place on the curve where it went from positive to negative, say this was a positive, this was a negative, then 0 would be a max. But it doesn't change at 0, so this is neither a max or a min. Minimum has to go from decreasing to increasing. Think about that. Y value is getting smaller, and then it hits a low point and goes up, get bigger. If it went from increasing to decreasing, y values are getting bigger, and then they start getting smaller, so it had to reach some sort of high point before it turns around. Okay, in order to figure out the location of my minimum, that's what it's asking for next, I am going to use the original function again. I want to know the y value. So I know that my minimum occurs when x equals 3. So I can say there's a minimum at x equals 3. Again, that's coming from this critical value. It goes from negative to positive at 3, so that means it's a minimum. If it went from positive to negative at 3, it would mean it's a maximum. Now I want to know the height of the maximum. So remember when we first started doing derivatives, we said that anytime you want the function's height, you go back to the f of x or the y equals equation. And you can plug these x values in here. And that will give you the function's height. It'll give you the y value. So I'm going to plug a 3 in for x. And when I do this, I get 3 to the 4th, that's 81. 3 cubed is 27. Okay, that's 108 when I multiply it by 4. And when I subtract these two things, 81 minus 108, I get negative 27. So the point 3 comma negative 27 is my minimum. There is no max. Okay, so I don't have to find the maximum value. Once again, if there was a maximum somewhere on this number line at one of these critical numbers, you would see it go from positive to negative. Positive on the left, negative on the right. Increasing on the left, decreasing on the right. Means you have to hit a maximum. Okay, concavity. Let's tackle this part first. For concavity, we're going to use something called f double prime, the second derivative. Okay, so if I want the intervals of concavity, I am going to use the second derivative. So f of x equals x to the fourth minus 4x cubed. F prime x was equal to 4x cubed minus 12x squared. F double prime x. So f double prime x equals 3 times 4 is 12, x squared. Subtract 1 from the exponent. 2 times negative 12 is negative 24, x to the first. Now, this is what I want to work with for the intervals of concavity. And the process is the same as what I did for the intervals of increase, where I was working with the first derivative. Only in intervals of concavity, I'm working with the second derivative. So I'm going to factor the second derivative. So I can take out a 12x, it's a common factor. Divide this by 12x, I would get x. Divide this by 12x, I would get negative 2. I set this equal to 0, and I am going to solve for my critical values. So 12x, I take each factor, set it equal to 0, and I solve. If I divide both sides by 12, I get x equals 0. If I add 2 to both sides, I get x equals 2. So my critical values are x equals 0 and 2. Now I'm going to make a number line, and I'll park it right next to the second derivative. I like to go with the factored form because it's easy to figure out the signs. And you don't have to use a number line. Some people make a little chart with put the factors in and they say whether it's positive or negative. I find the number line just quick and easy and serves the same purpose. Okay, so drew my number line, plugged these critical values. These were the values of x that made the second derivative 0. Again, there's 3 intervals from negative infinity to 0, from 0 to 2, and from 2 to infinity. I am going to test each interval, so pick a number between negative infinity and 0. Again, you can pick anything you want, all right, as long as it's greater than negative infinity or less than 0. It's obviously going to be greater than negative infinity. Plug it into the second derivative. 12 times negative 1, that factor becomes a negative. Negative 1 minus 2, that factor is a negative as well, negative 3. So I'd have negative 12 times negative 3, which would give me a positive. Okay, between 0 and 2, I'm going to pick a 1. If you plug a 1 in for x, remember you're testing the second derivative for intervals of concavity. 12 times 1 is 12. 1 minus 2 is negative 1. Positive 12 times negative 1 would give you a negative 12, or a positive times a negative is a negative. Test something between 2 and infinity, so I'll use 3, could use 10, 20, whatever you want. Okay, 12 times 2 is 24. Sorry, 12 times 3 is 36. 3 minus 2 is 1, so I have 36 times 1. Remember, I'm plugging the 3 into this. So 36 times 1, positive times positive, that's what we have. Now, there's 2 things. You can either be concave up, and concave up means that the tangent lines would all be drawn below the curve. And again, there's more information on concavity in your Teams app. But it's concave up wherever the positives are. So let's list those intervals. What's this interval right here with the positive above it? Okay, some people have a hard time telling what the interval is when there's negative 1s here. But remember, you're looking at the number line. The negative 1 is what I tested. I'm looking at this arrow pointing left and this critical value 0. So left arrow represents negative infinity, okay, to 0. And it's also concave up from 2 to the right arrow, positive infinity. So it's concave up where the positive signs are. Probably guess that it's concave down. And that would mean your tangent lines would all go above this curve. All right. it's concave down wherever the negative signs are. So it's concave down on 0 to 2. Okay. Now I want to find my inflection points. Well, there are inflection points anywhere the sign changes. So it doesn't matter that it goes from positive to negative or negative to positive. It did when we were talking the first derivative test. All right, negative to positive meant a minimum, positive to negative, if that occurred, would mean a maximum. Here, it just means there's an inflection point. So it goes from positive to negative at 0 and negative to positive at 2. That means I have 2 inflection points. So let's find our inflection point. One at x equals 0 and 1 at x equals 2. Now just keep in mind, anytime you want a point on a curve, you're going to use the original function. Okay, so first thing I'm going to do is I'm going to plug a 0 in for x. We've already done this calculation twice when we were doing our intercepts, but it's all good. I'll show it again. And here I'm going to plug in a 2. So let's go with 0. 0 to the 4th, 0. 0 cubed is 0 times 4 is 0. This would be f at 0 equals 0. So I have an inflection point at 0, 0. That was also the location of my x and y intercept. This time I'm going to do a 2. And f at 2 is going to equal 16, 2 to the 4th. 2 cubed is 8, times 4 is 32. So f at 2, 16 minus 32 is negative 16. So I have an inflection point, or another inflection point at 2, negative 16. So here's the move now, once we have all that information. And I'll go back up here and just show you that I've completed everything. Points of inflection. Remember, points, maximums, minimums, points of inflection, intercepts, we have to use the f of x equation. We use the derivative for the intervals of increase, and we use the second derivative for the intervals of concavity. Now here's what I want to do, is sketch this curve. I want to plot all points. Draw all asymptotes. Not applicable in this case for the polynomial. So not applicable for polynomial. And then we are going to use intervals of increase and decrease, along with intervals the intervals of concavity as well. Concavity to connect the dots, basically. So I'll show you what I mean. I have this one already drawn. So for starters, I would list my x-intercept at 0, 0, and the other one at 4, 0. There's my x-intercepts. There's my y-intercept, 0, 0. Okay, so the x and y-intercepts would go here and here. So try and picture this without this purple or this pink line. The next thing I would do is I would put on my minimum value. That's what I found next. That was at 3, negative 27. So 3 to the right, down 27. And then I would place my inflection points. There was an inflection point at 0, 0, and one at 2, negative 16. So again, picture it without the pink line drawn. Okay, but then we can use our intervals of increase and decrease. Now, I knew that this function was decreasing from negative infinity to 0, and then from 0 to 3. That means the y values are getting smaller, all right? Or my tangent lines, let's undo that and take that away. Look at my tangent lines. If I were to draw tangents anywhere along this curve, the tangent lines all have negative slopes. That means the function is decreasing, and that's what that first derivative test told me. Then it was increasing from an x value of 3 to infinity. So check out this portion of the curve. If I draw tangent lines on this portion of the curve, anywhere along that portion of the curve, it's not a great tangent line, but you get the idea. Those all have positive slopes. They're all rising from right to left. Okay, so I will erase those and just kind of highlight the last section or the last portion of intervals of concavity. So I have decreasing from negative infinity to 0, decreasing from 0 to 3, and then increasing from 3 to infinity. And I'm making sure to go through all of those points. I also have this portion of the curve where it is concave up. All right, look, concave up, as I said, the tangent lines would be below. So if I drew tangents on that portion of the curve, they would have to be drawn here. Concave up from negative infinity to 0, concave down. All right, concave down, I say it looks like a frown. All right, that means the tangent lines would have to be drawn above. And then once again, concave up from 2 to infinity. So it was concave up from negative infinity to 0, concave down from 0 to 2, and then concave up from 2 to infinity. So these points of inflection, it's like a little twist in the curve where it goes from being concave up to concave down, or vice versa, concave down to concave up. But in a nutshell, that is how you sketch a polynomial function. Start by plotting all of the points first, okay? From your intercepts to your maximums and your minimums to your inflection points, plot all of them, and then join your curve, or join your points with a nice smooth curve. And I'll fire arrows at both ends, but there's a very detailed sketch. That is what the function y equals x to the fourth minus 4x cubed looks like. That is a polynomial function. The next video will show you how to do a rational function. So a function that has or is in the form of a fraction.